All right. Hi, folks. I'm Steve. Thanks all for coming out. I'm the GM for Search at Elastic. I've been with the company for 10 years, which is sort of like forever in Elastic years. It's like dog years or something. Company's been around for 12. And I want to talk a little bit about some of the work we've been doing around sort of semantic search and vector search, specifically, and as if time allows, I may run out of time, but I've got a couple other sort of related topics around search that I think we can get into that would be interesting. To start with, many of you are, how many people are actually using us for search use cases, building an application, interactive? So for a lot of these, for a lot of these applications, like relevance matters, right? It's mattered for all of the applications that we've built over the years. You know, for user satisfaction, I expect to get good results back. I expect it will work, for all these different reasons, all these different use cases. If you were looking for a restaurant, you want to find one that's nearby, that matches your requirements, that gets good ratings, that has good reviews. These are the kinds of things that you expect out of systems today. And so relevance has always been important to the experiences that we build. But we've seen in just the last, the last year, the last 18 months, search has totally changed. For a long time, you were happy with just 10 blue links or something like that, where relevance was important. But as you switch from getting from a 10 blue links to getting an answer to your question, something else happens. And this is like a psychological thing that we've observed in a lot of the different applications and users as we watch. We see people trusting the large language models very differently than they trust the 10 blue links. When I'm a user and I see 10 blue links, I know what my job is. My job is to find the answer in the 10 blue links, to find the document I was looking for. That's my job. When I get one answer, I don't have a job. My job is just to read the answer and be done. And so psychologically, there's a lot more trust that users put on that one answer that an LLM gets back. And so it means it's that much more important that the answer the LLM provides you is the right answer. And so I actually probably should have included some slides on retrieval augmented generation. But one of the most important approaches that, for today, for how people take into account actual answers to actual information. If you're going to ask a simple question, is Thanksgiving in the US a holiday for our company? The language model doesn't know anything about that, right? The language model, you can almost think of it as a nice repository of world knowledge or something like that, but it doesn't know anything about your private data. It doesn't know anything about the restaurants or the reviews that are part of your application or part of your system. And so the language models are great with that world knowledge, but to get them that context, to get them the actual answer, you have to find the relevant data and the relevant documents and bring that back. And so that's led to a lot more pressure being put on this accuracy, this relevance side of search. And so as you start to go down the road of sort of relevance in search, that's where we've seen a lot more interest and a lot more focus on vector databases or vector search. So if you've seen any of the literature or any of the information around building these kind of Gen AI or RAG applications, they're all saying, hey, you need to start by getting your context into a vector database and start to run that retrieval. And so the vector database component, Elasticsearch is a vector database. We've had dense vector fields for like 5 years or something like that. And we've done a lot of work, I'll touch on that in a moment, to become really the best vector database, we believe. They all have different trade-offs, all have different levels of maturity, but we've put a ton of energy into it to become the best vector database. And what this allows us to do is semantic search. It allows us to search, to use a language model to encode the meaning of the sentences and the phrases into numbers, into vectors, into an array of 32-bit floats that represent the meaning of that sentence, of that paragraph, or of that document. And so vector databases are now a critical sort of part of the infrastructure for getting great search relevance, in addition to BM25. Now, I want to go deeper into Elastic as a vector database because we've put a lot of time into it, but we also recognize that as you build out these different kinds of applications on top of a search engine or a vector database, you need a lot of stuff to build your whole application. So at the core of a vector database, you have to be able to store the vectors. You have to have a way to store these arrays of numbers that represent the meaning in the documents. And so that's sort of like the baseline. And actually, there's a number of vector databases that just do that, and then they let you search them, and then they're done. But when you go to build an application, something has to create those embeddings for you. You have to take the text from the document. And as David showed just a moment ago, you have to chunk that. You have to separate that, maybe a large document, into chunks, where you can encode a meaning of those individual chunks. And then you need some model and have to run a model to go and do that. We let you do that directly inside of Elasticsearch. We provide support natively for our own first-party sparse encoder model called ELSER, as well as any model you can get off of Hugging Face. We also have an easy button for running a multilingual search model called E5 from Microsoft, which we optimized a bit. So this is some of the things that you need just to get embeddings, go from text to get embeddings to use the vector database. But then when you start to build the rest of that application, there's a lot of other things that you need. To get the best relevance, what we see is actually combining vector search with traditional lexical search. There's some things that like words are good at, like an exact match really means something. If I'm typing something, I expect to get the exact thing I typed for back. Whereas semantic search is really good for searching for the meaning of that word. If I search for car, I want to find auto, and I don't want to manually tune, synonyms or something like that to make it happen. And so in this way, having hybrid search really matters. Having the ability to choose, having filtering and fasting, all the things that you need to build your sort of complete application, that's what we're focused on providing. But a big area of investment for us has really been in this space. But we, as a mature search platform, we've provided all of these capabilities. And this is really what we think people need to build a full application with a vector database. But making Elasticsearch into a leading vector database didn't just happen. This is only recent, and I haven't even updated it for 8.16, but you can see the work that we've been doing over just the last couple of months. In the last, maybe this is about a year's worth of work, but this has become a huge area of focus for us. This is the fastest growing part of the use case for Elasticsearch for search. And so we put a ton of energy into it. I'm not going to go into all of the pieces of this, but I wanted to touch on just a couple of different angles because I think there's some unique work that we've been doing that will also help, I think, make sense of the complexity. So when I mentioned at the beginning, you have this these vectors that get created. So you take the text and you pass it to this language model. The language model, it's called an embedding model, and it takes the text and it turns it into an array of float 32 numbers. This is like a lot of numbers and a lot of memory that you have to hold all of those numbers. And so the idea of a vector search is just, I want to compare the vectors of my query against the vectors in all of the documents in the data store. And there's different techniques that you can use to make that more efficient because it can be a little bit expensive. If you imagine with the actual usage pattern of vector search, it is a highly random access kind of thing. You don't know where you're going to need to go on disk or in the data structures to go find the most relevant documents. And so there's a high random read aspect to that. So it doesn't do well if you have to go to disk. Disks don't do very well at sort of this kind of random seeking behavior. Even NVMe drives are really slow compared to memory. And so you have to keep all of these vectors in memory if you want great search performance in terms of just query speed. And so that takes up a ton of memory. And I'll show some examples in a moment, but it's a huge amount of memory. If you want to search a million documents, you're going to need like, I don't know, like a terabyte of memory or some crazy number. You're going to need a tremendous amount. And so there's techniques called quantization that take those 32-bit floats that represent those documents and essentially compress them in very simple ways down to, from a float 32 down to an int 8 or down even to an int 4. And so over the last couple of versions, we've added this sort of native quantization to Elasticsearch. And given the performance that we see, being both good in terms of throughput, losing very little in terms of accuracy and recall and precision, we've actually enabled this by default. And so when you go and use dense vectors, you're actually getting quantization on by default because that's going to give you the best sort of price performance, if you will, right out of the box. You get control to tune all of this, but you shouldn't have to. And so again, you get quite a bit of control here, but you don't have to use that control. Now, scalar quantization is good, but we keep asking ourselves, could we do better? So this is sort of a picture. This is just 500K. So this isn't even a million vectors. But for, and again, this is imagine the model had 1024 vectors for each one of those documents. And again, you can see here, we're already well over a gig just for 500K. Start imagining that at a million, imagine that at 100 million. It's a huge amount of memory that you would end up needing if you're doing the raw. So the blue is sort of the float 32, what typically comes out of the language models. The red is sort of the int 8 compression that we do. And then the yellow is int 4. Once you get down to int 4, you do start to lose a bit of accuracy, and you can sort of see that represented. But if you're going to have 100 million documents, this is 50 gigs worth of memory, even for I think it's the int 8 there. And so we want to do better. And again, I mentioned before, what we've done already is we've gone from float 32 to int 8. This is on by default. We give you the choice to go to int 4, but it has an effect on your recall. It has an effect on your precision. And so you want to be careful in using it. You could do scalar quantization all the way down to the bit level, but that, if you just do that, it is not a good idea to do. It really hurts your recall. It really hurts your precision. And you have to do a tremendous amount of oversampling just to get back to that base level of precision that you need to actually give good results to the user. And so just this simplistic of scalar, just like very simple math, just, and try to go from, turn the float 32 into a 1 or a 0, just in a naive way, does not work very well. And so we asked ourselves, could we do better than that? And so we're introducing something, and David mentioned it at the beginning, called Better Binary Quantization. The idea here is, can we apply some smarts to how we do the quantization to normalize it so that actually going all the way from a float 32 to a bit isn't that bad in terms of accuracy, and it is so much better in terms of throughput and performance that it's worth doing. And so if you go all the way down to the bit level, this gets us 32x savings in terms of the amount of RAM that you need. And if we can do this without losing too much precision, too much accuracy, we can actually have this be a really powerful way to query. And I think the images here are sort of captured a little nicely. So it's sort of like you can see how much you lose when you go all the way there. But if you were smart about it, if we can put the compression in the right places, if we can adjust it as we go, we can do a little bit better. And so with bit level, you can start to see this is almost looking too good to be true, because they take that 100 million vectors that was huge before. Now it's fitting all the way down into just 12 gigs of memory. So now 100 million vectors become easy to query just within a single server of Elasticsearch, when that would have been like physically impossible, or tens of servers if you were doing this in full precision vectors. The other thing that we tried to think about here as we were building this is to say, what is the effect of having this kind of quantization on indexing throughput? And so from left to right, you've got the float, so the original float 32s, the quantized to int 8, scalar quantized to int 4, or BBQ. And an interesting thing, even though we're doing more work with BBQ to sort of normalize these vectors to get the most value out of that 1 bit per dimension that we can, we still see a lower overall indexing time because the index is so much smaller and so much more efficient. And so even in terms of indexing throughput, we're significantly faster. And by using this technique and using this approach, we end up, there is a trade-off. It's not like everything's free in this world. And so there is a trade-off in precision and recall. So you need to be, it takes a little bit longer because you have to evaluate more results to get to the same result. And so the blue line here is bit level. Again, 32x less memory, and you can see we get remarkably close to the same level of accuracy or recall, which you see on the y-axis here. And these are different models. So this is E5, as I mentioned before. These are 2 different Cohere models with different configurations. But you can see different models have different sort of performance in terms of how they quantize, but you get a remarkable amount of recall for a very small amount of memory and a very small performance hit, because you are evaluating more documents. And so an interesting thing, if you were to go and sort of look at this, when you're doing this, you sort of need a sort of a 2-pass query, if you will. So what you do is you start by going, you say, okay, I want to return 10 results. In order to get the best 10 results, I'm going to go get 20. I'm going to evaluate, get my closest 20, and then see which of those are the best. And in this, when we're querying against this data set, which I think is a million vectors, here we're going to be evaluating 15,000 sort of candidates, 15,000 documents get evaluated. Not great recall, but you can see the latency remains really low. We can say, hey, let's actually evaluate 100 instead of just the 20. And you can see the recall goes up significantly with only a small impact to the relevance. And then you say, hey, let's evaluate 1,000 and then re-rank with more precision just 200. And it's still less than 100 milliseconds, less than 50 milliseconds, and we're able to get really high recall out of this bit vectorized data. So really tremendous in terms of what you can get from an accuracy perspective. One of the other approaches, there's sort of a legacy, not a legacy, but there's a well-established approach called product quantization that does something conceptually very similar. Takes these float 32s and has a way to compress them down into a single bit. And so that same 32x memory savings is available from products or other systems that have this product quantization implementation. We went and implemented product quantization and BBQ as a way to compare. We actually thought we were going to build product quantization. We saw some new research that came out that said, hey, BBQ and the approaches that we used sort of indicated that we might be able to get better accuracy by doing BBQ. We didn't expect to have better indexing throughput at the time that we started, but we sort of compared these two implementations with about a month or a couple months worth of engineering effort just to see how they work. And again, both have similar recall. PQ has some downsides in recall versus BBQ, but similar. And so when we go and we do the comparison, you can start to see what we get in the results. So the green here is BBQ, and the biggest difference that you'll see here is in the quantization time. The index time work that you need to do to create those, to essentially to quantize that, to take the incoming full precision vectors and compress them to a single bit, goes down by 13x compared to product quantization. Now, maybe there's more optimizations that could have been done on product quantization, but the significance with the same amount of time invested in both implementations, a well-known algorithm here, a new one here, very impressive in terms of the sort of indexing time benefit. And at the same time, we can see we can go a little bit faster on the searching side because we're just a little bit more accurate. So we only have to keep going until we get to 98%. And so we can exit earlier, if you will, to get that same level of accuracy. So this is a big deal in terms of what's possible now in a single server in a single system. That's a lot. Let me zoom out for a second. Just a couple of the other things that we've been doing that I think are kind of interesting. To get great performance for vector search, what it's doing is it's doing a tremendous number of these sort of numeric computations, and they are really, really parallelizable. And so we spent a lot of time trying to optimize right down to the hardware level. And I'll say there's, I don't know, like Elasticsearch is written in Java. There has been this, I don't know, this fake news for a long time that Java's not fast or something like that. It is fast, and the JVM actually does a remarkable job, automatically taking advantage of the hardware capabilities that are available, and it's gotten better at this over the years, obviously. But there's some things like this where we know exactly how we want to use the processor. We know exactly how to pack the registers to maximize the throughput. And so in this case, we actually got a boost from the JVM. They have the Panama APIs that allow us to directly and efficiently write like C code that we can go and execute really at the low level. And so we've actually written extensions to Java in C for each of the major sort of CPU platforms that look at the CPU capabilities and leverage the different kinds of sort of hardware level optimization. So SIMD, the AVX512, these kinds of things that let us do more in parallel allow us to get significant benefits. And so I mean, these actually have gone even further than just this, but 30%, query latency and indexing improvements, 3 to 6x faster when we introduced SMD. These huge improvements just through this focus on performance, and that's really what it takes to be a competitive platform these days in this domain. How am I doing on time? Do I have a couple more minutes? Okay, cool. All right. So that's on the vector database side, a huge number of improvements that we've been putting in there. If I take just a step back and touch on maybe one of the other things, and David, you sort of touched on this a little bit, I think, but one of the things is also how do I write and author queries? And how do I combine both a lexical search, a text search, with a vector search? We've had a feature in Elasticsearch called RRF for a while, the reciprocal rank fusion that allows you to essentially run both in parallel and combine them. And that has been useful and very powerful, but the syntax has been somewhat limiting for a number of different use cases for a variety of reasons. And so for that, we took a step back and said, what if we had a way to have composable queries? So you can run multiple queries in parallel and then score them and rescore them or re-rank them in multiple ways. And so we introduced this retrievers framework into the sort of Elasticsearch query DSL, letting you run multiple different kinds of queries. Here I'm running a regular sort of text query, lexical query. Here I'm running a KNN, which is a sort of a semantic search or a vector search query. And I'm able to combine multiple of these queries together in different ways. And so this framework, this retrievers framework, makes it much easier to sort of compose these into sort of more natural or approachable ways. And so you can start to see Here at the bottom, we're saying, let's get the initial results retrieved from both of the different approaches to querying, standard and KNN. Then combine them with RRF and then re-rank the results. And so in a relatively simple way, we've crafted a fairly sophisticated query and made it understandable and approachable in a way that was not really possible before within Elasticsearch. All right. So the last one that I wanted to touch on was ESQL. This isn't specific to search. In fact, we may see this actually show up in some of the other presentations and discussions on observability or security. But ESQL, this is a new query language that we're adding into Elasticsearch. Is anyone here familiar with ESQL so far? I know you are. I know you are. This is actually interesting. So we've had the Elasticsearch query DSL forever, right? This is like the language you use to query Elasticsearch. We've added other query languages over the years. So we have EQL, really good at sequence matching. We've added other languages over the years that try to simplify things in different ways. But we never really tried to say, let's make one language that's like made for humans to type. And if it's made for humans, actually language models are getting pretty good at typing it too, which is nice. And so this query language, it's not just like a language designed to just do what we already do, but better. It's designed to let us do some things that we haven't been able to do. So ESQL itself, So ESQL itself, it's actually not just a query language. It's actually a new query execution engine inside Elasticsearch. What we've done is we've taken Elasticsearch's query DSL. It doesn't really have like a query planner or query execution sort of a framework or something like that. There's no place that it stores intermediate results. It takes your query and it flings that query as quickly as it can to the individual shards on all of the data nodes in your Elasticsearch cluster, and then as quickly as possible gets those results back and gets them to you. Very little additional processing can happen in the way the classic query DSL has worked. In ESQL, we said, hey, there's some things we want to do that are hard today. I want a place to store intermediate results so I can then join something to that. I want to store intermediate results so I can ask another question of that intermediate result and another question, do multiple levels of that. And so we had to build an entirely new query engine inside Elasticsearch. Then you have to expose that to a query language. And then you need a UI and sort of an experience to sort of see that and to make use of that. And so this is really what we've been doing over the last couple of sort of, really it's like 18 months of development. And so I'll quickly go to a demo and I'll attempt the demo gods actually I won't because this is a recording. So, but if I go through this, I'll show you a little bit about how you can sort of craft these queries and what you can do. And it lets you do things that some of these things are technically possible with Elasticsearch today, but very difficult to do. And so if I look at this is actually very simple data. It's just a timestamp, a log level, and a message. That's it. That's all that's in the index. You can imagine I might want more than that out. But again, each of these documents has these different, just this very simple structure to it. And so what I can start to do here is I can actually go and start typing. Now, you'll notice right away, this is the index name, and then I start to pipe. And I get type ahead support right here. So this is a rich editor that can give me this type ahead support. And I can start to just compute some very simple statistics on the fields that I have, like the log level. And so if I go and I run that, you can see very quickly across this data set, I'm able to pull back, hey, let's take a look at the log level, info, error, warn, about the same across all of those. In the product, we've got this full documentation, so you can see all of the docs right there for you. A nice way to just have inline visibility to it. And now I can start to do some new things. And so you may be familiar with Grok. This is essentially a regular expression library that we've used in Logstash. It's available in Elasticsearch for index time enrichment. Now we can do this at query time. And so I can start to say, hey, look for the timestamp at the beginning, look at the log level, and then start to extract some of these other pieces. And as I do that, now you can start to see, just from what was a message field and a timestamp, I've now got multiple fields. And now I can start to do things with these fields. Like I can start to sort by them, and so I can sort of do these different kinds of things so I can see what are the errors. Or I can filter on that. So I can actually filter on one of the fields, which class. I can filter to the record accumulator and where the log level is error. And I can start to build up this richer and richer query just by adding a pipe on the results. And so it's sort of like you just add and extend and extend and extend. This is a powerful way to go and explore the data. If I take an example that's a little further along, we can also start to do things like enrich data. And so here, extracted some fields, I've looked at them, I've filtered them to just this subtype. I added another grok to parse it further because now I'm looking at a subset and I see things I want to pull out of this subset, so I can do another grok. Then I want to summarize by IP, and then I want to look the IP up with a host name from a different index. And so this idea of looking up this sort of query time enrichment, or almost like a query time join with the enrich function, gives you this ability to go from what are IP addresses here to, if I go ahead and run this, into host names here. And when I mentioned that it's the query engine, it's the query language, and it's the query UI, this is a big part of the query UI, this ability to say, hey, I've got charts right here, and I can go and I can edit these charts if I choose to. And so I can come in, I can look at the query history here, and then I can start to actually add this visualization, if I like it, directly to a dashboard. And so now, right from the Discover experience inside of Kibana, we were able to craft a fairly sophisticated query and sort of add that right to a dashboard. Now, this is fun. It's a phenomenal language. It's going to be a wonderful way to explore sort of log data and security data. But it's not just for logs, or it's not just for observability and security. It's also for search. And so we are in the process of adding search capabilities to ESQL as a language. And this is going to be fun. It's going to be fun for a couple of reasons. One, this is a language designed for people. And so it's going to be much easier to author a lot of the queries that today you have a lot of syntax to wrap around. So it's going to simplify some of the things in terms of how you write those queries. But it's also going to open up some new possibilities. I mentioned before that we have sort of these native inference capabilities, the ability to run language models directly or call language models directly from inside Elasticsearch. Imagine if you could pipe the output of a text query to say, hey, give me my top 10 results, and pipe that to a summarize function that calls out to an LLM to summarize those 10 results for you. Or imagine you could pass a chat to that and say, hey, please answer this question about these top 5 results. And this idea of being able to build these almost like a mini RAG pipeline, this sort of like experience directly inside of Discover, directly inside of a query, will really, I think, transform a lot of how people think about what you can use Elasticsearch for, and think about how hard or how easy it should be to build some of these applications. It should be easier. Spoiler. Huge amount of work we're doing in other areas as well. I won't spend as much time there, but a tremendous amount of work goes into making this engine and language work. But I did want to, I sort of alluded to this before. I'll put it up in big letters here. I do think this is an important one because when you think about that enrich command that I had up on the screen before, it was doing a lookup. In that case, it's doing it in a very narrow way, the special enrich policy you define. We want to have joins supported as part of the actual infrastructure, as part of the actual query language and engine itself. That opens up a bunch of interesting new ways to model data in Elasticsearch, whether it's a high update use case, whether you want to handle sort of this, what now you might do as a parent-child document, you can handle in different ways and get a lot more flexibility in how you model your data inside Elasticsearch. So this is still TBD, still coming, caveat, caveat, caveat. But this is very exciting in terms of what's possible now for building compelling applications on top of Elasticsearch. So with that, I think I probably used all of my time. And yeah, happy to take any questions if I've got a minute.